Okay, so we'll start this morning with a fairly simple but perhaps unusual question. So how many colours are there in the rainbow? At this point usually everyone says 7. Red, orange, yellow, green. People rattle them off.
Shades.
What?
Mixture of shades. It's a mixture of shades.
Yeah, I mean, people tend to rattle off red, orange, yellow, green, blue, indigo, violet and go 7. And some people get very upset when you tell them that might not be the case, you know. So visible light is a small part of the electromagnetic spectrum. Now I find it very hard to get my head around this, that the stuff that I see is the same kind of stuff that's coming out of the 96 FM tower and the same kind of stuff that my phone is using to communicate. For me, light and radio waves are two different kinds of things, but in reality they're the same thing, just at different frequencies, and humans can see a portion of this with their eyes. But it's a bit of a head wreck to think that the stuff in the microwave, you know, is the same kind of thing as what's coming into my eyes and being sensed. So we can measure light then we can talk about its frequency or its wavelength, and they're related mathematically. You can calculate one from the other. So the visible spectrum is roughly between 425 and 675 nanometers. So at the extremes then we have ultraviolet, which we can't see, and infrared, which we can't see. We can sense infrared sometimes. If there was a fire there, you could sense it, but you couldn't see it. And then this raises the question then, how many colors are in there? And so we've broken these up into red, orange, yellow, green, blue, indigo, and violet. And you remember in the last class we were talking about shades of grey and quantization levels. And basically somebody has decided that this spectrum here should be broken up, you know, into red, orange, yellow, green, blue, indigo, and violet. That those would be the quantization levels. So like between here and here, say, is one level. Between here and here is another level. Between here and here is another level. Between here and here is another quantization level. Now we can argue about where does green become blue, but in general we're looking at 7 quantization levels. And they're fairly arbitrary. I mean, we learn in school red, orange, yellow, green, blue, indigo, violet. And you know, even if you're from another country, you learn that just in a different language. It's pretty much embedded in Western culture. From time to time I've had mature students who, by virtue of their education, whatever path they took, hadn't been brainwashed into seeing red, orange, yellow, green, blue, indigo, and violet. And they were like, oh yeah, okay, but what are you talking about? Like, I don't get that from that, you know? So it can be, but it's learned. I think that's the important point. This breaking up of this into those areas is something somebody decided on, and then we all learned in school. So okay, where does red end and orange begin? That's tricky. You know, where does orange end and yellow begin? What if there was no orange? What if there was like just red, yellow, green, blue, indigo, violet? I mean, the sky wouldn't fall in, you know. We might have a reddish yellow or yellowish red, but you know, life would go on. You know, it could be yellowy red, you know, not the end of the world. And then where does green end and blue begin? That's a tricky one also. So most English speakers and most Europeans will divide this up into 7 colours. Red, orange, yellow, green, blue, indigo, violet. It's interesting that green and blue are huge. You know, and orange and yellow are tiny. So it's certainly not, the person who took this certainly didn't, you know, go every 50 nanometers of wavelength, we're going to do whatever. It's certainly irregular. And it's completely arbitrary. So if I was ruler of the world, I could decide, for example, that there was going to be Tak, Burble, Ip, and Grug. There's only going to be 4 colours in the rainbow, and that's what I was going to call them. And maybe kids would learn that in school. You know, it's completely arbitrary, the quantization levels that we have, the way we break it up. In Japanese, for example, there's a single word that can cover blue and green. So, a long time ago, if you look at paintings where people painted the rainbow, I mean, if you look at a child now colouring the rainbow, they'll be very upset because there might only be one purple marker or something in the rainbow, but typically they'll have red, orange, yellow, green, blue, indigo, and violet. They'll have the 7 stripes. If you look at paintings from a very long time ago, you'll find that there are only 4 colours when people represent the rainbow. And the colours were believed to be results of the interaction between black and white. The Greeks, for example, talk about black grapes and white grapes. The Greeks imagined that you've like white by day and black by night. So when the sun is setting, you see all those colours. Colour is something that's between black and white, and we know that not to be the case now. But so it was in 1699 then that Newton explained colour with the prism. So you saw that in science class. He originally had 11 regions. So in his original plan, there was scarlet, lemon yellow, golden yellow, dark yellow, green, grass green, sea green, blue, indigo, and violet. I do think he was onto something with the fact that the green was a bit expansive. Green was very big. He eventually settled on 7: red, orange, yellow, green, blue, indigo, and violet. At the time, there was this notion of a relationship between colour and music. And so it was accepted that some combinations of colours were harmonious. They went well together. If you had a mapping of colours to sounds, then it was understood that there were some combinations of sounds were harmonious that went together. And the idea was if you could map sounds to colours, then you could also have a system for harmonious colours. And because there's 7 notes in the musical scale, do, re, mi, fa, sol, la, ti, do, that's why we have 7 colours in the rainbow, because Newton was thinking along those lines. So the important point is that it's arbitrary. Certainly in day-to-day use we don't make the distinction between indigo and violet. You don't go into Zara to buy an indigo shirt and find they've only got the violet ones left and go, oh no, I really wanted an indigo one. You're probably just in the market for a purple shirt. So some people believe very, very strongly. They look at the rainbow and they do even see red, orange, yellow, green, blue, indigo, and violet, and they actually can even see the difference between the indigo and violet. And it's really ingrained in them. When in reality, in day-to-day use, we hardly ever do that. Similarly, men and women talk about colour very differently as well. This is you know what that is now. That's the kanji for that blue in Japanese. Okay. So I just wanted to make that point there, that the distinctions we make in the rainbow and the way we break it up are defined culturally, and they're somewhat arbitrary. Depending on how upset people get by that suggestion, that class there can take an hour, but hasn't taken an hour today, obviously. So we'll move on to look more scientifically, I guess, at digital colour and how it works. So we've seen that when we're digitizing a black and white image, that we identify each area, each region, and then we get the average lightness or darkness of it, and then we fit that into one of a range of values. So here there are 1, 2, 3, 4, 5, 6, 7, 8 ranges of grey. So whatever value would come out of analysing one of these areas here it would like fit into here or to here. It would be assigned one or the other. And then a pixel of that color would represent that region of the image. In this image, we've got 8 quantization levels. So this photograph, this image would be represented by 3 bits per pixel, for example. Okay, but how do we put numbers on color? That's a whole different thing then. I mean, we know green isn't the same as blue, but you know, like it's easier to say this color here in it has more white than this one, or this color here is darker than this one. In a grayscale, you have like lightness and darkness, and you can say this is lighter than this, and you could line them up. But how do we put numbers on color? That's the tricky part. Like, green is not the same as blue, but you know, is it more or less of what? You know, I mean, it's more green, but like apart from that, you know, what are we looking at? So how do you sort color? How can you put it in order? And that's tricky. So one thing we have is the hue, saturation, and brightness model, or HSB. So if we examine the visible portion of the electromagnetic spectrum and we have our rainbow, well then we could organize things based on where they would fit along the rainbow. So imagine sort of a rainbow scale with red at one end and indigo and violet at the other. Well, you could break stuff up and you could say, well, every so many nanometers, that's going to be a new quantization level. So this gives us a way to put color in order. And then when it's in order, the only issue then is how many quantization levels you have, how precise do you want to get, but you're on your way. So the position in the rainbow scale, as we call it, is the hue of the color. Now, there's more going on than just hue. I mean, if you look at the rainbow, there's no white and there's no black, for example. There's no brown. There's no pink, really. There's no grey. So there's more to color than just the rainbow. So all of these colors here have the same hue, for example. They're all in the blue part of the rainbow. These all have the same hue. They're all at the yellow end. These are down the purple indigo end, whatever. So it turns out that color can be diluted. So you can, it's what happens, for example, if you leave a magazine in the back window of a car and some of it's covered and some of it's not, and it starts to fade away. So you can dilute color. So saturation is the purity of the color. So highly saturated color is really, really pure. And then very low saturation is a pale color. No saturation turns out to be grey. It's like the chairs in this room, that blue is very highly saturated blue. Whereas the bin there, the top of the bin, is less saturated. Okay? So saturation tells you how pure the color is. And this gives us another way to quantify color. So here, those green chips, they all have the same hue, but the saturation is different. Okay? Again here, just changing the saturation of the color. Now, it turns out then that hue and saturation aren't enough. You need one more variable, one more way to describe it. So all these things here have the same hue and saturation. But what's different is the brightness. It's how much light there is in it, how light or dark it is. So you could imagine you have a light bulb that is a particular color, particular hue, you know, particular saturation. It's very strong, pure color. And then if you had it on a dimmer switch, you could turn it up and down. And when you turn it down, well, it's just black, the light's off. When you turn it up fully, then you get to see its color. So we have hue, saturation, and brightness. Okay. So those three values then can give you an accurate description of a color when you combine them. Hue is often expressed as a color, as a wheel, and it's a position on the wheel. So it goes from 0 around 90, 180, all the way around back to 360 to 0. So it's around in the circle, around on the wheel. So we usually express that as a value between 0 and 360. So that wheel representation is convenient visually, but also the fact that we've got 360 degrees, then that tells us really that perhaps for hue, maybe 100%, or even 256 might not have been enough in terms of quantization levels. So we do like to specify the color a bit more precisely. Saturation is typically expressed as a percentage. So 0 is like pure color, and 100% is pure color, and 0 is gray. And then brightness, we're on familiar territory when it comes to brightness. That's just the lightness and darkness. And so 100% bright is light, and then 0% brightness is black. Okay? And so you see something like this. So you have hue going around here. Then the saturation is the point on the radius, how far out you are from the center. And the brightness here is this slider up and down here. So if we were to go into something like PowerPoint and just draw a color chip there, you can do this in an awful lot of any number of apps, applications. So I'm just going to go in there now and change the color. Can I fill color here? Oops. And so here you get a color picker. That's quite small. Oh, there we go. No. So depending on the operating system you're in, the color picker will vary depending on the application you're in. But just crank up the brightness here. So here, as I move around the circle, okay, we're seeing the different hues. And you notice that, look, it goes red, orange, yellow, green, blue, indigo, and violet. So you can see there that the trip around the circumference of the circle is like a trip along the rainbow. Okay? As we move in closer to the center, the color becomes less pure. So you see that pink, for example, is red with the saturation turned down. So as it tends towards white, we pass through pink. So here along the point along the radius, we're modifying the saturation there. And then finally then, this third slide. So you can see you need three variables. You need, if we, in the future when we have 3D displays, your hue, saturation, and brightness will be a cube, and there'll be hue on one axis, saturation on the other, and brightness on the other, and you sort of pick out the one that you want. But when we're representing two dimensions, we need a separate slider along here. And so then as I change the brightness here, this is our full-on bright pink, and as I go down here, it gets darker and darker and darker. It just becomes then tending towards black. Okay. So what you could do there is you could open, I was going to say open up Photoshop, but I mean PowerPoint will do just as well. And no, you can't actually see the values here, that's the only thing. If you open it up in Photoshop, you'll see it'll give you the actual values, tell you what they're called. So it'll say like this is whatever degrees, this is whatever percent, 50%, this is 50%. So you could take down the numbers associated with the color. Might even be able to do that. You can do that in this version of PowerPoint as well, and you can see the numbers, but you don't then get to see the wheel so it's not as intuitive. But you see the numbers here. So this shade of shocking pink here is 320 degrees, 82% saturation and 100% brightness. If I turn down the saturation, it gets paler. Okay, so have a poke around there to get a feel for hue, saturation and brightness, and how you can pretty much represent any color. Now, HSB, hue, saturation and brightness, is the most intuitive of the color schemes that we have, because we're kind of familiar with the rainbow. You know, we know that, you know, there's a scale there that we're familiar with in everyday life. Saturation, you know, is strong or weak color, so that's something we can get our hands on. And brightness and lightness and darkness is something we're very familiar with. So hue, saturation and brightness is the one that most closely resembles how humans deal with color, how we understand it, how we even perceive it to some extent. So that's very handy. Of course, not the most widely used, but that's the reason we have it, is that it's the most natural. It's the one that maps most naturally to our everyday experience.